Hi, my name is Nicholas Karate.
Hi, my name is Madison Matson.
Hi, my name is Kara Walton.
Hi, my name is Stanley Wong. In 2005, Hurricane Katrina hit the southeast coast of the United States, and the effects were devastating. Over 1,200 deaths and $125 billion worth of damage. Around 9,000 residents took shelter in the Louisiana Superdome, which quickly rose to over 15,000 as search and rescue continued. There was a lack of supplies and hygiene and high rates of assault and crime. When the levees broke, residents were again displaced and moved to the Houston Astrodome, totaling around 25,000 Katrina victims in one location, where conditions got worse every day. Today, natural disasters are still an issue that we face. A recent study found that 43% of US homes and condos are at high risk of natural disaster, while another study found that there were 3 times as many natural disasters between 2000 and 2009 as there were in the 1980s. If these trends continue, we need to act fast in order to prevent another situation like we had with Hurricane Katrina. That's where we come in. Here at BrickCycle, our goal is to create sustainable building material out of waste plastics that is consumer friendly so that in times of emergency, victims can easily access these materials and build sheltered homes.
On screen are the 7 standard classifications of plastic. Our project aims its focus on recycling 3 different types of plastic. Number 1, PETE, number 2, HDPE, and number 5, PP. As a potential startup company, our material can come from a variety of places, including waste collection sites, recycling bins, landfills, or even individual households. The incentive behind plastic waste utilization, as opposed to disposal, stems from the scarcity of space and cost for landfilling. Our company can take this unwanted plastic and transform it into a durable material on site for storage and use.
Our team recognizes that shelter from weather and shelter from crime should not be a luxury good. The purpose of our prototyping and our process design is to create an easily accessible form of shelter that doesn't rely on having a high enough income or enough savings to get by. The end goal for this design was to create a finished brick and to test it for strength, insulation, and density. When COVID-19 became a global pandemic, we had to stop our prototyping and we quickly switched to a paper process and paper brick design. However, we did not let what we had accomplished in person together go to waste, and a lot of our process is based off of the results that we were able to obtain from prototyping.
An integral part of our project was building a prototype that met the functional requirements of a construction brick. Going into the building stage, our goal was to create a brick out of different types of used plastic. It was evident that our biggest obstacle was reaching a high enough temperature and pressure to promote fusing within the plastic and being able to control those conditions for an extended period of time. We tackled these objectives by iterating through 4 different experimental setups: heating the plastic with a clothing iron, heating with an iron and wrapping the plastic in aluminum foil, cooking the plastic in a pressure cooker, and melting the plastic in a toaster oven. All experiments tested a mix of plastic types 1, 2, and 5. In the first setup, we tried melting the plastic together with an iron and a baking sheet to distribute the heat evenly. Only type 2 plastic melted with this process, so we determined that we needed a way to reach a higher temperature. Our next set of experiments then wrapped the plastic in aluminum foil to achieve more efficient heat transfer. This resulted in better fusing between plastics 2 and 5, but made type 1 plastic brittle and failed to produce one cohesive block. To achieve a higher pressure, we conducted our next set of testing using a pressure cooker. While this gave us a convenient way to control the operating conditions, it took much longer than the other experiments and thus was ruled out as a viable option. This led us to using the toaster oven, where we could easily manipulate the temperature. By heating a mix of pellet-like pieces in a metal mold, we fused together all 3 types of plastic into one solid brick. By using a heavy rock to apply pressure during heating and cooling, we were also able to control the shape, resulting in flat surfaces on all sides. This set of experiments confirmed that it's possible to form a functioning brick out of recycled plastic and prompted the integration of a brick mold system into our overall process design.
This is our general flow sheet for the overall process. The process starts with the incoming plastics we talked about earlier being dropped off into our plastic tank TK101. After these plastics will go through a separator S101 and sorter S102 to be taken by conveyor belts to their respective pretreatment tanks. Here, a solution mixed with water will be used to cleanse the plastics. However, before the plastics are sent to the crusher, to be shredded to a certain size, they must be dried with an airflow as well as checked and cleaned of any remaining dust particles, as this might interfere with their ability to mix and combine later in the process. After the crusher has gotten the material into the form necessary for proper mixing, the plastic is sent to a holding tank where it will stay until a mass ratio of 1 to 2 to 1 plastics of PETE, HDPE, and PP is reached respectively. After this ratio is reached, the plastic will flow down a chute to the mixing tank TK108, where the plastic will be mixed and placed into a mold. Once the plastic is secure in the bottom of the mold, it is taken to the heating vessel HE101 inside of a fume hood where it will be compressed with the top portion of the mold and altered by temperature and pressure until a solid material is made. Now, I will take you further in depth on the mechanisms of our mold. The purpose of the metal mold in our process is to allow the melted plastic to conform to a brick shape with interlocking components. Each brick mold is designed to produce multiple plastic bricks. Once the plastic is mixed, it's placed in the bottom half of the mold and sent to the heating vessel to be heated to a melting temperature. Inside the vessel, the top mold will compress down onto the bottom mold to pressurize the set plastic. The top mold remains compressed until after the plastic has cooled. Then the bottom mold is sent out of the vessel where the solid plastic is removed by a vacuum tool and sent to distribution. The bottom mold is then cleaned and sent back to be filled with plastic once again.
While plastic bricks are a functional and environmentally conscious alternative to traditional bricks, it's critical that they also be economically feasible to produce. The costs of building and operating the process plant were compared against the potential sales. For plastic bricks to be marketable, they need to be similar in price to clay bricks, which are around 1 cent per cubic inch. Based on the sale price of PETE, HDPE, and PP, the cost of plastic bricks would be around 2 cents per cubic inch. With a throughput of 2,880 bricks per day, the process is profitable with a net earning of around $667,000 per year. Additionally, plastic bricks are interlocking and don't require the purchase of extra materials to hold them together during construction. This, along with the economic analysis, confirms that plastic bricks are a cost-effective solution for temporary housing.
It is our team's hope that this project will be useful in 3 ways. 1, providing not only an economically feasible but also sustainable process that utilizes these plastics to build cheaper homes. 2, uses these bricks to decrease the cost of building a temporary home for people affected by disasters or that belong to low-income communities. And 3, discourages plastic degradation in the environment, which contributes to climate change. Plastic can be an economically feasible alternative to traditional bricks or stucco materials like we commonly see homes from built in the desert. There are many characteristics that contribute to the feasibility of this process, including an interlocking brick system, free construction materials, and having a long lifespan. The interlocking brick system allows for the bricks to snap together, decreasing the need for a skilled mason or cement to hold a home together. The interlocking feature also allows for easy construction of corners. The excess quantity of plastics in the United States allows for the construction materials to be free or purchased at a low cost from waste management companies.